Hey guys, welcome to another tutorial. In this video, I'm starting a new series of implementing deep learning papers. So we will implement very basic paper and we will go to very state-of-the-art papers in later videos. So if you are interested in the series, follow along with me and subscribe the channel also. And in this video, I'm starting with the AlexNet architecture, which is a very basic and released on 2012. I recorded the video very slowly and I didn't notice that, but I would recommend you to go with 2x or 1.5x speed to get better understanding. And it's a very long video, about an hour, and you can finish it about 40 minutes too. Let's get started. Hey guys, so we can get started in this. First, we will gonna read this paper and we will implement this later with code. And this is the ImageNet classification with deep convolutional net paper. So one thing I can say to you in this, that I'm gonna use Pytorch library in this. There's also a famous library also called TensorFlow. TensorFlow is also a good library, but in a couple of past years, Pytorch has become really famous, and current state-of-the-art models are like kind of implementing with Pytorch. So this paper is just about classifying ImageNet dataset with deep convolutional neural network. So the abstract is really simple. They have like given some like modern techniques to classify or construct a deep convolutional neural network. And I think it's really basic and simple model comparable to today's state-of-the-art models, which are really advanced like GANs. This model has 60 million parameters, 650,000 neurons. I'm recording this video in mid or end of the 2022. So there's a GPT-3 model which has about 1.5 billion parameters, if I'm right. Probably more than that, I think. So this is the GPT-3 has a really big model, and it's like a real human, you can say. Like it has some kind of restrictions and limitations too, but like GPT-4 going to be really advanced, I think. But this is really good paper to implement if you are starting in deep learning and implementing paper. And as I said in the starting of the video, we gonna implement a lot of papers, and we'll upgrade our difficulty, and we will go into what we call deep neural networks in a couple of videos in this series. But you have to follow along in this series, so subscribe the channel and subscribe it. And so the introduction is simple, like you can read the introduction, but I'm going to directly jump to the main section, so the main points which I got from that thing. So in introduction, they have like they have given how they have, what are the new techniques they have used, or which are really beneficial from previous state-of-the-art models. And like they have also kind of faced some difficulty in this, like because this architecture is really large and deep, so they face this because of the size of our network made overfitting a significant problem. So the network is really large, so they faced overfitting. So if you don't know about the overfitting, what does it mean? So I can just give you the rough idea of what's overfitting. Overfitting means the overly fitting the data, or like where the model does not able to generalize well, where it started memorizing the things, so it does not able to perform well enough in new data. So you can think like generalizing or memorizing means that where it does not see the patterns or fundamental patterns in the data, rather than it starts memorizing things or looking just the data or making that overfit. If I will draw, you can get more understanding of it. So let's suppose this is a kind of a graph I'm going to draw. I'm sorry, I'm really bad at drawing, but yep, I think I can try, even though. So this is a kind of data, you can say. So this is data is distributed, and okay, so I need to fit the best line in it. So neural network is just about, or machine learning is about fitting the best line or fitting the best plane, whatever you can think into the dimensions. So like I can fit the line. Let's suppose, what's the color? Red. Let's take a red. And if I'm going to fit the best line, like what is going to be the best line in it, where the loss is really minimum, loss is basically going to be the distance between these points from that line is going to be really really minimum. So I think I can do like this, something, this is going to the best fit line. So yeah, I'm going to erase this. And what is the overfitting means here, which just means that you have overfitted the model over the data. So the line is overfitted over the data like this. So that's a really big problem in large models, that where the models start memorizing things rather than generalizing things. So they have used some regularization techniques like dropout layer to reduce the overfitting. And so the next thing is like they said our final networks contain 5 convolutional and 3 fully connected layers. So it's a really good information. So I have also highlighted with some kind of things like some problems with red, and some of the features of the models like with blue. So I think I'm gonna write down in the code so you can look at how I implement the paper also. So let's read a models.py first. So we can write in the comment that it contains about 8 layers, contains total 8 layers with 5 cons and 3 hidden, or you can like dense. So they have given how they have trained their model. They have written like our network takes between 5 and 6 days to train on 2 GTX 583 GB GPUs. So it's a lot of time, 5 and 6 days. Today we have a great GPUs, so it's not gonna take that much of time. But they have also introduced some of the data parallelism technique. So we'll also look at this thing. And the data set, they have also said about, or given the introduction about the data sets. The data set contains about 1.2 million training images with 50,000 validation images and 150,000 testing images. And like they have used mechanical track to I think human labelers using Amazon mechanical turk. So they have also labeled this thing. So we have also given a label. So this paper is, or this tech, what we're gonna use is in this is using supervised learning. That means we're gonna use labels to train the model. The main information that they have downsampled the all the images to 256 x 256. So what does it mean? That like all the images like contains different set of different resolutions. So they have downsampled or upsampled images to a fixed resolutions, because when you train the images in the GPUs, you're gonna train it in the batch. So in the batch, when you multiply or do matrix multiplication, so there's some kind of what you can say limitations in the matrix multiplication, that you need to be well defined dimensions, or a specific dimension to be multiplied those matrices. So that's why you have to use a fixed amount of fixed resolution of images within the batch itself, but they are going to use in the whole training set. So the next thing is the architecture, and the architecture is really important. And when you're implementing the paper, because that's the whole thing you're implementing, the whole architecture. So in the first, they have used ReLU nonlinearity. ReLU you can see as an activation function. And activation function is like that something, there's a couple of more activation functions like tanh and sigmoid, but they have used ReLU because there's a couple of reasons they have found. Like ReLU is really faster than uh, tanh, and a couple of reasons also, like primary concern is preventing overfitting. So the effect they are observing is different from accelerated ability to fit the training set, which we report when using ReLU. So that's why like probably they have used, or we're gonna also use ReLU, but it's not about implementing the same paper. We're gonna use the same set of rules they have introduced, but you can try also tanh if you have a time of like 6 days to train. but uh, but I think they have also tried a lot of things. That's the whole research is about, researching or experimenting with different set of things. and you can trust them that this is the really best thing they have applied. I don't know about the ReLU, so I'm gonna introduce a little bit about here that ReLU is just like taking the maximum of, this is the ReLU functions, and f of x equals to max of 0x means that if it gets the value, uh, like if it gets the x value, and if x is positive, then it returns the positive value, like because that's going to maximum. But if it gets the negative value, then 0 going to be the maximum, so it turns all the negative value to 0. So the graph of this is looks like that. Wait a minute. Something like this. And like this. Okay. And all the negative is going to be 0. So this is a really good activation function. It also has some limitations because after that we are going to calculate the gradients of it during backpropagation. So when you have a very large negative values, and when because of the negative values, it's going to turn, or really going to turn this values to the 0, and the 0 is just nothing, like it doesn't add any value to the model, it doesn't gives any information. So if you calculate the gradients of 0, it's going to be the 0, and it doesn't add any information to the weights, and it can't update anything to the parameters. So that's why there's a couple of variations of ReLU, like ReLU, and in couple of papers like in what we're gonna implement later, you will gonna see the leaky ReLU thing. Leaky ReLU is simple, like just add some variation rather than like turning all the negative values to 0. It has some kind of set of slope here, and yep, it's like that. I think we can move on to the training on multiple GPUs, and multiple GPUs is like they have introduced how to train or how to use GPU parallelizations, or use 2 or 3 GPU at the same time to make the training faster. So in Pytorch, we have given a kind of a data parallelism class. We can use it, and we don't need to worry about all the things how they have used all the techniques, because we just need to call the one function that is going to take care of all the GPUs. That's what I like about the Pytorch. It's really easy to use that library, and yep. So that's the whole training on the multiple GPUs, and uh, there's a couple of more things in the architecture that we're gonna look at, that is the local response normalizations. So if you don't know about the what is normalization is, or why we use normalization, so normalization is just means that input normalization is used for to prevent them from saturating. So let's suppose you have a very saturated data values from -1000 to +1000. So it has a really saturated, it has a very saturated data and have a very large range. So we use normalization to reduce that range and make it small, because let's suppose you have a range of 0 and 1, from 0 to 1, then it's easier to train the model, and the training going to be really faster when you calculating the gradients and updating the parameters, because when you have a kind of small range, then the training going to be faster. That's the whole thing about the normalization. And there's a couple more in the detail how, like there's a couple of more reasons too about the normalizations, and a couple of more techniques, like there's also a batch normalization, but they have used local response normalizations. So here they have written like denoting by AIX, activity of neuron computer, by applying kernel I at position xy, and then applying the ReLU nonlinearity. So xy is basically the coordinates or the pixel location of the kernel, and the ith is the which kernels, because kernels means the channels. So if you know about CNN networks, you know how the channels are distributed in the images. So we can apply the normalization over the kernels at the xy position, and this is k is a kind of a constant, or kind of you can say like it prevents from when the alpha is 0, and the sum of that, basically the whole term is 0, then it prevents it from getting non-defined. And the alpha is basically the normalizations or local response normalization constant, and we're gonna sum it or square, and there's a beta value also. You can look at more how does it work. I will give you the whole paper of it in the descriptions, but what it does is basically just apply the normalization and rescale the value at a set of range. So here n is the adjacent kernel map to the same spatial position, and the capital N is total number of kernels in the layer. And they have given some kind of constants like k equals to 2 they have used, and they are saying like constants k and alpha and beta are hyperparameters whose values are determined using a validation set. So like they have already tried some of the things and decided to go with that constants. So x equals to 2, n equals to 5, alpha equals to 10 to the power of minus 4, and beta equals to 0.75. So we don't need to worry about that thing really right now. Like we don't need to implement the whole equation from here. We can use the class, or Pytorch provides that thing. So directly we can put that values in that class and we get the whole equations right from there. And that's fine. Like, but you need to understand how that really works, the thing, to get some understanding and tune the parameters if you wanna like make it more better. And so that's a whole look response normalization, and normalization is really good technique to doing in the after basically the convolutional layers. There's also overlapping pooling thing, so we also apply pooling layer. So let's draw something so you can understand better. So I'm going to use the 4 into 4 kernel map, or not 4 into 4 but 2 into 2. This is a 2 into 2 kernel map. 10, 12, 3, and this is a kernel maps, you can say, or kernel this is also one name, also feature map. So kernel map or feature map, they are really same. And so we're gonna apply pooling layer over there. This is the results of the after the convolutional layer. So we get the feature map, and then after this feature map we have to apply, or we probably gonna apply the pooling layer, or mostly the max pooling. So in the max pooling, how it's worked basically, let's suppose I'm going to choose green. We will use the max pooling layer or max pooling grid, going to be around 2 into 1 grid size, and the stride is 1. So in max pooling we're going to extract the maximum of it, like 10, and the next, because the stride is 1, and so it's going to be the next thing, and it's extract 12. So at the end we have the like brightest part of the information, or brightest part of the image. That's what we're gonna need to use it. We need to use or apply or basically learn these features, these brightest features, to understand the image, because there's a couple of things in the images, like backgrounds. If the background is black, value is going to be really bad, like going to be 0. So if we're gonna use that 0 2, then it doesn't really apply, or it gives a lot of information. So it's just making that grid really large and taking lots of time to train that thing. So that's why we use max pooling to extract the high information of the image, or brightest part of the image, so we can get some understanding of the edges, lines, and some patterns in the image. So that's the whole thing about the overfulling. So we can look at the overall architecture. The net contains 8 layers with weights. So we have already written that in the VS Code, or in our main file, the models file. The first 5 are convolutional, and the remaining 3 are fully connected, which are dense or hidden layers. And there's a couple of things also, like the output of the last fully connected layer is fed to 1,000 base softmax, which produces a distribution over the 1,000 class label. So we have used softmax, like they have used softmax activation functions in the last layer after fully connected layer, the last fully connected layer. So softmax is basically, it combines or like all the activations and provides a probability. So if the softmax has a vector size of 1000, then it produces a distributions over the 1000 class labels. So we will also write this in that thing. So softmax activation function after class layer. Then there's a couple of more things in this, that response normalization layers follow the first, second convolutional layers. So follow the first and second convolutional layer. So we will also write this, follow only the first and second convolutional layer. Response normalization layers only apply only to first and second, after basically apply after. Cons there. And yeah, so both follow both response normalization as well as, and there's a couple of things like before that. So and max pooling layer of that kind described the section 3.4 follow both response normalization as well as fifth convolutional layer. So follow max pooling and also in the last, in the fifth, in also after, oh no, what's happening after the fifth con layer. That's it. Response normalizations and max pooling is kind of described in section 3.4. The relative nonlinearity is applied to the output of every convolutional and fully connected layer. So that's it. Apply value to really after every con layer. Every con layer or every convolutional and fully connected layer. But here it is given like applying every convolutional, applied to the output of every convolution and fully connected layer, but we have seen here like in local response normalization. So after basically the max pooling, after every max pooling, so because we can say that the convolutional going to be the whole thing, like the convolutional layer plus response normalization and max pooling. The three layers going to be the full one CNN layer. So there's a couple of more informations here given. The first convolutional layer filters 224 x 224 x 3 input image with 96 kernel of size 11x 11x3 with height of 4 pixels. So I think like there's I can just put that thing here, what's the exactly they are saying, or like the first convolutional layers filters this, so with 96 kernel size and with we're gonna use try 4 pixels. So you can see like here the whole architecture of it. It's easy to understand, but they have also divided into two GPUs, so it's look more kind of distributed. So the next convolutional layer takes the input the output of the first convolutional layer. So like they have also written or in the back bracket that the one convolutional layer contains the response normalized and also the pool layer. The output of the first convolutional layer going to be the input of the second convolutional layer. And so this is the whole CNN layers. The first layer's input dimensions is going to be 224, 224, 3, and output dimensions 11x11x3. Kernel is going to be 96 and stride. And here also the fifth layer also going to be like this. So you can read about these things more, and I think we can just get started. And there's a couple of more things we can look at in this paper, that is reducing overfitting, how they have reduced the overfitting. Like they have applied some data augmentation. Data augmentation, it just means like you have applied some transformations over data to generate more data. So like the model can learn the different types of same images, different set of variations of same images, like some kind of rotated image, cropped image, or some kind of flipped image. So it can get more understanding of it and learns better to generalize the thing rather than memorizing the thing. And that's the first way, or like the basic way we can reduce the overfitting, but it's not going to be the whole uh, like we can't reduce the whole overfitting because the model contains a lot of parameters. And so that's why they have also used a dropout layer. So dropout is basically, because of there's a lot of parameters in the layers or even the whole architecture. So during the training, we can apply dropout layer over over any layer, like linear layer basically, to drop some kind of neurons on that layer. So there's a one parameters which is the probability p parameter. Neurons going to be dropped by the probability 0.5. So it's about a half neuron is going to be dropped, and it's going to be random. And in the details of learning, they have given some kind of how they have trained the model. Like they have used weight decay or gradient descent. They have used batch size. So this is really good information. So you can say like this. I'm going to highlight, like they have used batch size of 128 examples, momentum 0.9. So momentum in the SGD or stochastic gradient descent means like it's basically triggers or accelerates the gradients to go in the right directions. So it finds a optimal value really faster. And they have also used a weight decay. Weight decay is just like they have said they haven't used weight decay as a norm regularizer, but mostly weight decay is used as a regularizer. So here they have given us some kind of equations to it, like in the momentum, like vi plus 1, that is 0.9. They have applied momentum constant of it, and into vi is a momentum variable. Into this thing, epsilon is kind of learning rate, I think. So yeah, epsilon is the learning rate, and this is the gradient or the average over the ith batch di of the derivative of the objective with respect to w. So with using the weight decay and momentum, they have like approach to the last level, like wi plus 1, that's the next weight. They have uh, updated the wi with this vi plus 1. And there's a couple of more details you need to know. If you want to know, I can give you the like couple of links in the description, that how the why we use momentum, or how what's the maths behind the momentum, so you can look at too. And like they have also given us some information about how they have initialized the weights. So we have initialized the weights in each layer from a zero mean Gaussian distribution with standard deviation 0.01. So we're gonna initialize with standard deviation 0.01. Initializing the weights means that you have some kind of initial weights to start the model, start training the model. So with using standard deviation 0.01, and we have like initialized the neurons bias in the second, fourth, and fifth convolutional neural networks, as well as in the fully connected hidden layers with constant one. So, but I think I can get started over this, and let's start implementing the paper. There's not much information about here. It's just a conclusions or qualitative evaluations of how well the model have performed. So we can just get started coding. That's the best part. I love it. So I've already created the models.py, and you can get started and follow along with me. So import torch, import torch, nn as nn, and then we're gonna create a class, which is going to be our model, AlexNet, and then dot module. and def init, and there's self number of classes, number of classes. Then you have to call the super because we have inherited nn.module, and super AlexNet so cons. So here in this, we're gonna use sequential layer to use the or to construct the convolutional layers, and so nn.sequential, nn.conv2d, and in channels, the first layers is have the channels 96, I think 96, yes, 96, and the kernel size going to be the 11 because output dimension is that 11. So output dimension just means the kernel size of it, and stride is going to be 4. And we can apply also padding here. After that, we can apply local response norm, but here that after the convolutional layer, I can define also what is going to be the output size or output dimensions going to be. So here, so after this convolutional layers, the output going to be the n is the like the batch or number of images in the batches, and 96x55x55. So it has a formula here, like I can show you. And here it's a Pytorch one. So probably it has the like kind of the edge output, that is the height of output the height and the output the width. So you can use this formula to calculate the output dimensions of the image, or basically the feature map. And then we can apply nn dot local response norm, and the size is going to be the 5 over the kernels, and nn dot max pooling, then max pool 2d kernel size 3, and stride we're gonna use it too because in the paper they have given, I think output's also going to be, I can also paste output of it, and then we can apply the relay. Then also again we're gonna apply the nn dot con2d, and here we haven't used this thing. I think I've made some mistakes because I haven't, it's going to be the out channel, sorry, out channels, sorry about that, really apologize the same. And in channels going to be the 3, because why we are using 3, because when you are feeding the image to networks, it's probably gonna be have, or the images we are going to use, it mostly have 3 kernels, and 3 kernels means RGB, red, green, blue, and this output channel is going to be the input of the second convolutional layer. And we're gonna not use the padding here, and stride is going to be the simple, that is 1. So if we're not gonna use stride, it's the default is 1. And the kernel size is here 5, so you can see the 5 here, the kernel size. Response normalization I apply only to first and second layer, so we also apply the second layers also. And then there we have maxpool 2d, and I've also made some mistakes here, like I have to output, why I'm forgetting output channels, and here it is the 256. Am I right? Yes. And the maxpool 2d, the same kernel size with same stride, and follow the max pooling layer of a response normalization layer. So after the response normalization layer, we have max pooling layer, and it's going to be the, like, after that we will not gonna use it max pooling and not response normalization, but we're gonna use max pooling in the last layer, which is after the fifth con. And the output going to be of this con layer is the nx 256 x23 x23. And after this convert or max pooling layer, the output going to be like this. Then what we have nn dot value, and another thing that we can also apply that on, because this we have implemented two convolutional layer till now, and consider this as a one con layer, because they have also, like in paper, they have also considered this as a one con layer. And after applying the value, and then the second con layer, and after applying the value, so just copy this thing, and 256 out char is going to be 348, kernel size is going to be 3, and and the dimensions going to be, the output dimension is going to be nn dot nx 348 and 99. So nn dot value, apply value after this, because we don't have to apply anything here, fourth, and it's the dimension is going to be just, because we haven't changed the kernel size, so the dimension is going to be the 7x7 with 348, and the same apply value after that, dot value, and another con layer here. So another con layer is going to be the 5 here, 5, and we're gonna change the in channels. So this is the fifth layer, I think, isn't it? This is the fifth layer. So fifth layer we have kernels 256, and in channels 348. So after that we have to apply max pooling too here. So nn dot max pool 2d. The kernel size is the same, isn't it? Or anything we need to change? I think we can apply the same kernel size here. And let's try 2. So the thing, the dimension is going to be this. And after that, I think we need to use the value, dot value. This whole set of layers, the 5 convolutional layer, going to extract the whole feature from the image. So we have downsampled the whole 224 by 224 images to 2 by 2 matrices. So this is really great that we extracted the features, then we're gonna apply or use that features to classify the images. Classifier, and here what we're gonna just do is nn dot sequential and then dot flatten. What flatten does is it's like going to be like that. So the output dimension is going to be nx1024, because if you multiply these things, the output going to be generated like this. And then we can apply the dropout layer too, because we're gonna drop some neurons here in the linear layer. So 0.5, and then nn dot linear in features. In feature is going to be 1024, and out features going to be like they have given the values. I think we can look at more in there. 4096 4096. So 4096 neurons are the output features. And then we can use the relief because we have to use apply relief every after max pooling layer and for the connector layer. So relief is a good bar, isn't it? Like kind of it is everywhere. And nn dot dropout again. Then nn dot dropout again with p equals to 0.5. Nn dot linear, you can apply 3 linear layers in features 4096, and all features going to be the same. And nn dot value, nn dot dropout, p equals to 0.5, and nn dot linear layer. I think we don't need to apply the dropout because in paper they have given only apply the first and second linear layers. So nn dot linear and in features 4096, out features 4096. Then we can use the softmax. It's gonna give the probability over 1000 classes. Softmax. So this is the constructor, and I'm going to go really fast after that because the video is going to be really long. And so let's do it fast. Then we can apply. We have to construct a one function also here, that is initializing the parameters, because we have seen here in the paper that we have to initialize it. What is the where? Here is it. Details of training. So init parameters, and so here what we're gonna do here is for layers in layer cell.clone and cons Hey guys, so we have created the model, and what we're gonna do next is use this model and train that model. So like I also like download the data sets, because to train that model we need our data sets. So ImageNet Mini we have a download which contains 1000 classes and about 1.2 million images. It is about I think 6 GB. So we can create a train.py, and from models we can start importing things, but we're gonna need to use it. Models import AlexNet, import Pytorch, import torch.nl as so that's the modules we're gonna use. And Then we can define some constants here, and GPUs equals to 0. This is a list of GPUs. It contains ID. So if you have multiple GPUs, you can put IDs of each GPU. So you can use data parallelism. And there we have a 90 epochs. In the paper, they have used about a 90 epochs. And train dir, ImageNet, mini train val dir equals to ImageNet mini val and image dimensions 2 to 4 and pad size equals to 128 and L weight 0.01, weight decay 0.0005 as given in the paper, and the momentum constant is 0.9. Checkpoint dir equals to checkpoints and slash device equals to qdown if pause dot qdown dot is available calls CPU. And if you got the seed, torch dot initial seed, we're gonna store the seed to get to know, because seed is used to generate the random number, so we're gonna store the seed also, so we can, if we want to generate the same random number, so we can use the same seed. Create model equals to AlexNet number of classes dot to device and here we can train with multiple GPUs, so we can define a data parallelism with Pytorch, and model equals to torch dot nn dot parallel dot data parallel. Here we can define a model, and device IDs equals to GPUs. And then next we can train the model, so we can look at what are the architecture of the model. And the next thing we can do image augmentation and transformation. So data transform equals to transforms dot compose transform dot center crop image dimensions transforms here dot random horizontal flip. And then transform dot to tensor transforms dot normalize mean equals to 0.5 and 0.5. I think that's the good. as ed equals to 0.85. So I'm gonna give you the information of what we have done so far. Basically, we have done like some image augmentation. So image augmentations, as I already said, like to do some transformation over the images. So like we have done center crop, and there's also random horizontal flip, and then we did some transformations like to tensor, because we need to convert the like array or list of pixel values to tensor, so we can use the GPU over the tensor. And then we also normalize our pixel values. So as we know, the normalize means that preventing from saturating or scaling all the values to a small range. So basically, if you think about or go into more details about the pixels, then you find that pixels contains the range from 0 to 255, where 0 is the very least and the black color, and 255 contain the brightest. So from this range, which is really large, 0 to 255, we're gonna normalize this from 0 to 1. So we can easily transform, make some activations or convolutions over these images. So the next thing we can do, prepare the data sets. We have defined some kind of transformations, and we have composed that whole transformations, augmentations, using transforms.compose class. And the next thing we can use, or the next thing we can do, prepare the data set. Prepare the data sets. Training data sets and data sets dot image folder. Train dir data transform. Val dataset equals to datasets image folder train, sorry, val dir. And the next thing, we can load the dataset loader using data loader class, and train dataset. We can define batch size here. And there's one more thing, that is number of workers. Workers equals to 8. Maybe this thing doesn't work in your device, because like in my device, number of workers equals to 8 doesn't work. So try to switch it different values like 2, 4, then try to some like switch it different values and try to use it. If something works, then it's good. Otherwise, you can just set it as default, whatever the default value is going to be. And the val loader, data loader, val data set. I think we can just copy it, and val loader, val data set, and then whatever the thing is, that same. Then we can use or define optimizer optim equals to torch dot optim dot sgt model dot parameters, and mixing lr l rate momentum So this thing we have defined the initialize our optimizer, and the next thing is loss function. and criterion. Some of the people also say cost function, so don't confuse it. Some way written as cost function or criterion also. Optim dot, sorry, torch dot, oh, I'm writing it wrong. nn dot cost entropy. So in the paper, they haven't mentioned anything like what are the loss function they are using, but we can use criterion here because it's a very good loss function in the domain of classification. And there's one more thing that I haven't, I think, covered, which is here in the learning. They have also mentioned like they have used equal learning for RAs, which is just a manual throughout the training. And the heuristic which we followed was to divide the learning rate by 10 when the validation error rate stopped improving with the current learning rate. So it means that like they had decay the learning rate by 10 when the validation error rate stopped improving with the current learning rate. So here we can use the last scheduler which decays the learning rate after every X step. So we can here define decay the learning rate and LR scheduler equals to torch optim step LR optim step size equals to 50 and gamma equals to 0.1. This gamma is a multiplicative factor, so after every 50 steps this gamma going to multiply by the learning rate, so it's going to divide the learning rate by 10. And that's all, and we can start the training now. So finally, total steps equals to 1 and training for epoch in range epochs for step x, y, and enumerate train loader x, y equals to x dot 2 device y dot 2 device. What we are doing is pushing this to the whatever the device we have. If we have GPU, we can compute these variables on the GPU, or if we have a CPU, we can stay with that. Whatever, we can also compute this with that CPU. But if we have a GPU, probably it's going to be faster than really faster than CPU. Refreshing gradients. Optim dot 0 grad. So here what we have done is like refresh the gradients for every, like whenever we start or predicting or doing forward or backward propagations, we set the 0 grad, means that we refresh all the gradients and start the gradients from new after that. And forward pass, in forward pass we basically predict the model, predict the value which is y value by giving x to the model, and then taking loss. Criterion takes predictions and the actual y. So we have y here also in the training loader. Y contains the labels. So here we are, as we are using supervised learning, so we use labels to train the model. And after loss, taking loss, we're gonna do backward pass. Loss dot backward. then taking step. So in backward loss, in the backward pass, we compute the gradients, and then in the taking step, we're going to update the parameters. That's all. And then what we can do is like if total steps, we can like kind of bring some information here. So if total step percentage modulus 10 equals to 0, print step basically step. And second, we can also print the loss. And we can update total steps plus equals to 1. That's it. And then saving the checkpoints. And in the saving the checkpoints, I've already a code, so I can just try to like grab it here and paste it. So in the checkpoint saving, we are just defining the checkpoint path. That's checkpoint directory. We have already like initialized the constant variable, and we are creating a file name with model checkpoint, and after model checkpoints, we're gonna specify also the epochs of it. And here we are saving as a pickle format. So that's a whole checkpoint path, which means the actual file of the checkpoint. And after that, we're gonna initializing the states of it. So states means that how much the epochs and the total steps and optimizer. So we are in optimizer, we are optim.stateDex. We're taking all the values or all the information from the optimizers, whatever the current optim contains. And then also same as we are doing with the models, model.stateDict, which are gonna give us a lot of like parameters values. And as we are already defined a seed and initialize the seed, so we can also store that seed too. Then we are saving the checkpoints using torch.save and giving the argument as state and the checkpoint one. That's the whole thing. And I think that's all. We can just train it and see what we have. Python trained apply. And what is this? Oh no, some errors. Okay, that's it. That's the thing. First step. Okay, there's also some mistakes here. Some typos, commas, whatever this is, torch vision. Okay, torch vision. Torch vision. That's it. Yeah. Let's see. Torch vision trans. Okay, transforms contains. I'm so sorry, guys. I really apologize for the typos. I'm really doing not good work. Okay, that's it. Oh, we have also one more error, that is content. I don't know why this is happening right now, but constant. So that's all. And I think I have also made some mistakes here, that I have taken this as this going to be 2, because 0 1 2 we're gonna count it as 0. So 0 1 2 3 4 5 5 6 7, and it's going to be 7. So that's all. Let's see, is there anything we need to do? Torch vision to transfer has no attribute center prompt. So there's a one more typo here. There's a lots of typo error here. Yep. Let's see what else we have. Transform is not defined. Transform is not defined because it is transforms. Let's see. Okay, yeah. I hope things are going good now. So we have printed like what we have defined. Okay, so there's a one more error that is got unexpected keyboard weight decay. So weight decay. Let's see what is. Okay, weight WEIGHTDECAY. Okay. Finger cross. Mat 1 and mat 2 shapes cannot be multiplied here. Okay, I think like if we use 2 to 7 here, like because I have used this thing, let's try this. Yep, it's working. So I have calculated this output dimensions wrong. So like probably with corresponding to 2 to 4 image dimensions, I've used 2 to 7 dimensions, so it's working now. I think you can look at using that formula, like using 2 to 4 and probably this. So you can get to that level and apply that thing also in linear layer because as I define in the last layer of dimensions, I calculated with 2 to 7. So guys, finally it's now training and we have created the whole architecture of the AlexNet model, read the paper, implemented with code, and also training that model. And I'm gonna stop here because it's gonna take a long time to train that model. But I hope you learned a lot from there, that how to read the paper and how to implement that thing. So I hope we will see you in the next tutorial. See you guys.